Okay, it is rather long, but we're going to be talking about the transformations, different kinds of symmetries, how to change a graph, what does that do to the equation, or if we change the equation, what does that do to the graph? So first off, we are going to talk about three types of symmetry. So one type of symmetry is if you can reflect it across the y-axis and the left and the right sides of the graph match. One of the easy ones for that is a basic parabola. We graphed a lot of these last year. We had you identify what is the line of symmetry. So if the line of symmetry is the y-axis, it is symmetric about the y-axis. When we are doing symmetry tests, that means you must do the algebra to prove that they are symmetric. You can look at the graph to have an idea what kind of symmetry does it have. But it's not okay on the homework problems to just look at the graph and say, oh, it's got this symmetry and not that one, and so on. You've got to do the algebra. What that means, for a graph like this that is symmetric about the y-axis, it doesn't matter whether I do x or the opposite of x, they will have the same y value. So I can change x to minus x, do some algebra, and see if I get back to the equation that I started with. So if I have y equals x squared and I do the test, instead of x times x, I want minus x times minus x. But if I simplify that, minus times minus does what? Is positive, so this becomes x squared, so that matches. So this is symmetric with respect to the y-axis. Now it's a little bit weird. If I change the x's, it's symmetric about y. And be sure when you're writing these, I can tell your x's from your y's. Don't get so sloppy that they look alike. I need to be able to read it. Similarly, we can have symmetry about the x-axis, and in that case, we are going to change y to minus y, do the algebra, and see if we get back where we started. So one that I could do for that would be a sideways parabola. X equals y squared. It is not a function. But do you see how this looks like the top and the bottom halves match each other? To do the algebraic test, we change instead of y times y, minus y times minus y. Then we simplify and see if we get back where we started. So minus y times minus y is, come on guys, what is it? Minus y times minus y is y. It's y squared, which is the same as where we started. So yes, it is symmetric with respect to, since we changed the y's, with respect to the x-axis. The third kind of symmetry is symmetry about the origin. That means you could put a thumbtack in 0, 0 and spin your graph around, and somewhere before you get all the way around 360 degrees, the shape looks just like it did before. So a lot of times it will be, if you turn it exactly upside down, it looks exactly like the same shape. The labels are kind of off because now you've got positives where you had negatives, but you're not worrying about anything that's labeled on there, just the shape. Sometimes if you turn it 120 degrees, the shape's going to match up. Those will be symmetry about the origin. There are two ways you can check that algebraically. One way is to change both x to minus x and y to minus y, do the algebra, and get back where you started. The easy way is if you have done the algebraic test for x-axis and got yes, and you've done the test for symmetry about the y-axis and you got yes, then you can automatically say also symmetric about the origin. But that's the only exception. Yes, yes, means yes. Yes, no does not tell you if it's yes or no. No, yes does not tell you if it's symmetric about the origin or not. No, no does not tell you yes or no about the origin. You're going to have to do this double change to check that. So here's one example with a circle. Does that look like it's symmetric about the origin? Does that look like I could put a thumbtack at the origin and spin the circle and the circle would still look the same? Yeah, no matter how many degrees I did or didn't turn it. Does it look like the left and the right match each other? Does it look like the top and the bottom match each other? So this one looks like it's got all three kinds of symmetry. If we did the test just for the origin, changed x to minus x, y to minus y, then we need to simplify. What's minus x times minus x? What's minus y times minus y? Did that get me back to what I had before? So it is symmetric with respect to the origin. If I did the test for x and y axes, if I changed just x to minus x but kept y the same, minus x times minus x would be x squared. I would have kept the y squared, so I would have had symmetry about the y-axis. Same thing if I kept x squared and just changed y to minus y. So it would have passed the symmetry with respect to the x-axis. So this one had all three. Do you remember the function family y equals x cubed? What does that graph look like? Caleb? So kind of like that snaky shape. So something kind of like this. Okay, does this one look like it's symmetric about the y-axis? Nope. What about the x-axis? But if I spun it exactly upside down, would the shape look the same? So we suspect symmetry only about the origin. So if we changed y to minus y, and if we changed x to minus x, so instead of x times x times x, we had minus x times minus x times minus x, I'd have minus y equals minus x cubed. If I multiplied both sides by -1, would I be back where I started? So that is the algebraic proof for symmetry with respect to the origin. So does that make sense? Okay, now we're going to shift gears and get ready to start thinking about transformations when we are sliding things up and down and left and right, or when we are reflecting entire functions. Instead of just one function looking at both sides of it, what if we want to take and compare two functions? What do we have? So before we do that, let's talk about some of the kinds of functions that we know that then we might be able to figure out graphs just by, oh, that's just a transformation, instead of having to go through a lot of point plotting and things. So one of the function families that we've known for a very long time now is your linear function family, and your most basic linear function is y equals x. And of course, another function family we were just talking about is your parabola. So I've got 1, 1 and 2, 4 here, drawing a nice parabola as best I can. Arrows on both ends, y equals x squared, and those are our quadratic functions. The one that we just talked about would be our cubic functions. Just label that cubic. And that's going to go through 0, 0, 1, 1, 2, 8, -1, -1, -2, -8. On the left side of the y-axis, it is concave down. It's opening down, so it's kind of like a skinny upside down parabola. But as soon as we get to the origin, it shifts and it is concave up. So it is like, sort of like part of a right side up parabola. Another good one that we've worked with would be y equals the absolute value of x. So a slope of +1 on the right and a slope of -1 on the left. One we haven't done a lot with yet, but I could have 0, 0, 1, 1, 4, 2. I could have half of a sideways parabola so that it's a function, and that would be y equals the square root of x. And we have also done quite a bit now with reciprocal functions, the basic hyperbola, y equals 1 over x. And we've done enough of those by now to know they look like that. And I didn't give you a grid on your paper, but we've been doing quite a few of exponential growth or decay. I'll just draw the growth one here. Y equals k to the x, where that goes through 0, 1, and we could end up shifting that up or down or left or right or flipping it upside down. So we'll start having some homework problems with transformations of that function family as well. And then the bottom of this page, we're going to write down what happens in equations when we do have those kinds of transformations. We went over this a little bit several lessons ago. We're going to go over it again now just to make sure that we've got that in the notes. If we have one parabola and we want to reflect that across the y-axis. So before I talk about the algebra, if I had this blue function and I flipped it to the other side of the y-axis, instead of the vertex at -4, 0, it would come over to +4, 0. Do you see how the red one is where the blue one has been flipped to the other side of the y-axis? The algebra of that is change x to -x in the equation. So last year when we did some of these, we usually got them in vertex form. Y is x plus 4 squared plus 0. And so if we plotted that, it was the opposite of what's on the inside. The vertex was -4, comma, the same as what's on the outside here. So if we flip that, we're going to change x to -x. So instead of x squared, I'm going to have -x times -x. And I'm going to have a -x here, which means this one becomes x squared minus 8x plus 16. So this one becomes y equals x minus 4 squared plus 0. So it has a vertex of the opposite of this -4, so +4, comma 0. I could have changed this x to a -x, and I'd get the same thing. I'd have -x plus 4 all squared. It doesn't quite look the same. This was x minus 4, that's 4 minus x. But if I factored so here's what I'm squaring. If I factored out a -1 from this right here, that would leave me x minus 4. And if I squared the -1, I'd have a +1. And then I've got my x minus 4 squared just like I did here. So the rule for reflecting across the y-axis is to, if you have your original function, change the x to a -x to get your reflection across the y-axis. Change x if you're reflecting across y. Everybody okay with that one? That's probably the longest one. That's the one I go into the most detail on. Whoops. To reflect across the x-axis, we're going to change y to -y. And we've seen that with when we had y equals x squared was right side up, opening up. Y equals minus x squared was opening down. But if I had changed y to -y, and then multiplied both sides by -1, I would have had it the way we're used to thinking about it. So all we did here was put a minus sign in front of the whole thing. So If this was our original, changing y to minus y, multiplying both sides by a minus 1, so minus in front of the whole thing, is a reflection across the x-axis. Reviewing our translations again, if we want to go to the left, we change x to x plus h. Going in the negative direction, we do a plus on the inside. Going to the right, so going in the positive direction, we do a minus h on the inside. If we want to go up, we do a plus on the end or the outside. Now, I think your book says if you add 1 on the right, the way we usually write the y equals, we could subtract that from both sides. So instead of y equals, we could have had a y minus. So we could also change y to y minus something. So we could add on the right or subtract on the left, and it's the same thing. If we want to go down, we subtract at the end or on the outside, or your book says it, if we subtract on the right, that's the same as adding on the left, or change y to y minus k. And we've done those before, that's why I just went through these real quickly as a reminder list for this lesson. A couple of you are still writing, and then we'll flip over to the back and work through our example problems. Is it okay for me to move on to those? Okay, so first example says use symmetry tests. That means do the algebra. See something like this on the homework, you may not just look at it and write down what you think. You may look at it for your prediction, but you still need to show me all of your tests for the 3 kinds of symmetry. So when you look at that, give me a prediction. What kinds of symmetry do you think it will have? So what? So symmetric about the y-axis. Do you think it'll be symmetric about the x-axis? Think it'll be symmetric about the origin? So we're guessing just the y-axis, so let's do that first. To test for y-axis, we need to change x to minus x. So we'll keep y. Instead of x times x, we'll have minus x times minus x, and we'll keep the minus 3. Minus x times minus x is just x squared. Does that match? So symmetric with respect to, since we changed the x's, the y-axis, making sure I can read that that's a y. Started to do all of the tests for me on the homework. So now we're going to change y to minus y. So we have minus y equals. We'll keep everything else the same. And is there any way I can make that be y equals 4? Let's see, if I multiply both sides by -1, so I get y equals, I get negative 4x squared plus 3. There's no way that's going to match. So as you suspected, not symmetric. With respect to, we changed y, so the x-axis, making sure I can read that that was x-axis. For origin, we need to try to change both at the same time. So I'll change y to minus y, and instead of x times x, I'll do minus x times minus x. So I have minus y equals 4x squared minus 3. Exactly what I had here that didn't work. So it's not going to work here either. So not symmetric with respect to origin. Questions with that one? Yeah, yeah. You have to do all three one way or another. Okay, what about this one? Give me your prediction. Ashani, what do you think? What kinds of symmetry do you think that might have? So it looks to you like maybe top and bottom match and left and right match. What about origin? Do you think you can spin it and it matches? Looks like if you turn it exactly upside down, the shape would look the same. So our prediction is yes for all three. Let's see if that's what we got with the algebraic tests. So if we check for the y-axis, we need to change x. So instead of x, it's minus x, and we leave everything else the same. And what does that simplify to? 6x squared plus 2y squared. Does that match the original? So symmetric. With respect to, we changed x, so y-axis. Okay, now let's change just the y. 6x squared, and instead of y, it's now minus y that gets squared. And that is 6x squared plus 2y squared equals 12. That also exactly matches. So it is symmetric. With respect to, I changed the y's, so this one is the x-axis. And then origin, therefore, symmetric with respect to origin. The only time I can skip one is if I do origin last, and the other two have both been positive, have both been, yes, it is symmetric with respect to x-axis and y-axis. So that's the only time you don't have to actually do all three. Any questions with that? Okay, let's shift to some of our transformations. You'll have problems like this where they give you one graph and give you its function. So this on the left is the graph of y equals the square root of x. Then they are going to tell us that we want to reflect it in the y-axis. So if we flip it across the y-axis, it now looks like what we have over here on the right. And now we want the equation for this new graph. If we reflect in the y-axis, that means we have to change x to minus x in the equation. So if we take this and change the x to a minus x, we now have y is the square root of the opposite of x. That does not mean we're taking square roots of negatives. We're not talking about imaginaries. Notice for the one on the left, the domain was only the things that were not negative. We could only put non-negative things inside of here. Over here, the domain is everything that's not positive. It means for x, I can only put in non-positive things. So if I take the opposite of those non-positives, I don't have any negatives, and it works. Everybody good with that one? Okay, next example. Still starting out with the square root graph. But now, let's reflect it about the x-axis, and let's shift it. So we're going to do two things to this. So first, if we only reflected it about the x-axis, that means we change y to minus y, which means we have y equals minus the square root of x. Then to go 3 to the left, what did we write down we do? We add or subtract, inside, outside. Sharon, what? So if we want to go to the left, we add, and where? To the left, we add inside. Up and down, we add on the outside at the end. Left and right, we add on the inside. So we change x to x minus something. So for that, we are going to change the x to x. If we're going to the left, we're going to add on the inside. So that means we have y equals, instead of x, we have x plus 3. So y equals the opposite of the square root of x plus 3. I kind of stumbled my way through that. Everybody good with where we ended up, though? Okay, let's move on then to example 5. So if we were asked to graph y equals 1 over x, we just did that with function families. We know that it looks something like this. If we try this, we're not going to actually do the graph. This one didn't specifically ask us for that. But if we wanted to move it 3 left and 4 down, we'd take everything that's known. We'd take 1, 1, and we'd move it 3 left and 4 down. So -2, -3, I think. We'd take -1, -1, and move that 3 left and 4 down. We would also move the asymptotes. The vertical asymptote would move 3 left, so now it's x equals -3, and it would move 4 down, which means it just slides up and down on itself, so that doesn't really change anything. So we'd have a vertical asymptote at x equals -3. The horizontal asymptote would move 3 left. Well, that doesn't do anything, but 4 down does. That new horizontal asymptote would be y equals -4. So can you kind of picture that whole thing moved? Okay, we are going to do the new equation. 3 left means we do what, Ian? Plus or minus inside, outside? Add on the inside. And 4 down means we're going to do what, Hope? Subtract 4 on the outside or at the end. So if we are doing this on the inside, that means x changes to x plus 3. And then we do -4 on the outside. So our new equation is y equals 1 over x plus 3, and then a -4. Now, the order that we do these can make a difference in what the equation looks like. If we had a parabola, if we reflect it in the x-axis, so we're going to turn it upside down, move it 4 to the right and 2 down, it is now upside down with a vertex at 4, -2. So let's come up with the equation for this one. If we reflect in the x-axis, we have the -x squared. If we go 4 right, that means where we had the x, we need to add, or going to the right, we need to subtract, so x -4. And then to go 2 down, we need to do a -2 on the outside. What we did last year, the minus means it opens upside down. The vertex is 4, -2. However, if I change the order on this whole thing, if we take the parabola that's right side up, move it 4 right and 2 down, and then flip it, now the vertex is at 4, +2 instead of 4, -2. So the equation needs to look different. So if we take y equals x squared, shift to the right 4, we change the x to x -4. Down 2, we do the -2. And then, if we reflect it, we change y to -y, which means we have a minus in front of the whole thing. Or we have y equals minus x -4 squared plus 2. So what we did last year, the minus sign says it opens down. The vertex is the opposite of this, so +4, comma, the same as this number, so 4, 2. So far, so good? Okay, almost finished for today. I want to get just a tiny little bit out there about absolute values, and then we will stop. If we had just the black graph, y equals the absolute value of x. If we reflect that about the y-axis, does it look any different? If all we do is reflect it about the y-axis, we still have that black absolute value graph. Let's think about what happens algebraically, though. If we reflect about the y-axis, we need to change x to minus x. But you guys just said that that graph has to look exactly the same as the absolute value of x graph. Does that make any sense algebraically? If you take the absolute value of a number and you take the absolute value of its opposite, do you get the same thing? So when you're doing some of these, if you have the absolute value of minus x, it is okay to say that is the same thing as the absolute value of x. So then if we wanted to get the pink graph, if we wanted to shift one up and one left, what do I need to do for one left? If I'm going in the negative direction, Colin, I need to add on the inside, and one up, I also add on the outside, and that would be for the pink graph. So any questions with what we have done today?